I want to start today with a bit of a cognitive calibration
Oh, I like the sound of that.
because we spend so much of our lives operating in this middle ground. We think in minutes, hours, meters, kilograms, the human scale.
The comfortable scale.
Exactly. But I've been looking at this mountain of research we have for today, and frankly, my brain is struggling to find a baseline. So I'm just going to throw a few numbers at you just to kind of disrupt that sense of normalcy.
I am always up for a little disruption. Let's hear them.
Okay. So think about patience, the concept of patience. A snail can sleep for up to 3 years.
3 years.
3 years. That's a hibernation cycle that's longer than most undergraduate degrees.
It's a process called estivation, actually.
Yeah.
It's not just a long nap. It's a profound metabolic shutdown to survive extreme conditions. But yes, 3 years is an incredible length of time.
It's just unbelievable. Okay, then switch gears to biological engineering. A giraffe's neck, just the
Yeah.
peck, can grow up to 2 meters long.
That's 6.5 feet.
Yeah, that's a taller vertical span than I am just to reach a leaf.
And just think about the heart required for that. The hydraulic pressure needed to pump blood all the way up that column to the brain is a marvel of evolutionary cardiovascular engineering in itself.
It's a biological skyscraper. Then you switch to human engineering, the Eiffel Tower. We see it as this single graceful silhouette,
Sure. An icon.
but it's actually a collection of 2.5 million individual rivets holding 7,300 tons of iron together.
Each one hammered in by hand. It's a monument to brute force assembly as much as it is to design.
Right. And then the timestamp of the cosmos. Saturn takes 29 Earth years to complete a single lap around the sun.
A single Saturn year.
Meanwhile, down here in a rainforest, a red-eyed tree frog is using these incredible six-sided toe suckers to stay perfectly motionless, completely ignoring the rotation of the planet, let alone its orbit around a star.
It is a chaotic mix when you list them like that.
Mm.
I mean, you're jumping from gastropod metabolism to orbital mechanics to 19th century French engineering.
I know, but there's a common thread here.
The numbers.
The thread is the data, the numbers.
Uh-huh.
And that is the mission for this deep dive. We are looking at the universe from the very edge of the cosmos down to, well, the cellular level of a tree, all through the lens of numbers.
It's the right way to do it.
We're basing this on a huge stack of sources, including our world in numbers, to try and measure the miracles we usually just take for granted. We're going from the Big Bang to exploding trees.
There's this tendency to think of numbers as the dry part of science. It feels like the homework you have to do before you get to the cool concepts.
Totally. The math test.
Right. But I'd argue it's the opposite. I think numbers are the only way we can actually access reality. The human brain isn't wired to understand infinite or microscopic in any intuitive way.
We're wired for, what, 1 buffalo or 5 berries?
Precisely. Numbers allow us to build a bridge across that conceptual gap. They let us, touch the age of the universe or feel the crushing pressure inside a neutron star, even if we can't truly comprehend it.
They're the translation layer.
They absolutely are.
So here's the roadmap for you listening. We aren't just going to list a bunch of facts. We're going to try and inhabit them. We'll start at the very edge of the universe space, the infinite scale.
The biggest of the big pictures.
Then we're going to zoom right in to the extreme physics of the stars, focusing on our sun. From there, we'll enter the solar neighborhood, look at the planets, then land on Earth to discuss the violence of its geology.
And it is violent.
And finally, we'll end with the just plain strange mathematics of living nature.
From 13.8 billion years of cosmic history to the six-sided toe of a frog.
Let's do it. Let's start at the absolute beginning, the Big Bang, the origin point.
The moment time itself starts the clock.
Our sources pin the age of the universe at approximately 13.8 billion years. Now, that number has become so standard in the scientific community that I think we forget how incredibly hard it was to get there. It wasn't until the Planck satellite data that we really dialed in that precision right.
That's absolutely right. For a long, long time, the best we could do was a huge range. It was somewhere between 10 and 20 billion years, which is, not exactly precise.
A 10 billion year margin of error.
Exactly. But 13.8 billion is specific. It implies a very specific chain of events. And the most critical numbers in that chain, right at the start, are the temperatures.
I was looking at the thermal data for the first few moments of existence. It completely breaks any thermometer you could possibly imagine. The sources say that just 1 second after the Big Bang, The ambient temperature of the universe was 10 billion degrees Celsius.
10 billion, that's 18 billion degrees Fahrenheit.
That's a number that it doesn't even mean hot anymore in the way we understand it.
It doesn't. At 10 billion degrees, you aren't just talking about heat. You're talking about a state of matter where physics, as we know it, is still struggling to establish the rules.
So what does that look like? What even exists at that temperature?
Well, the key is what doesn't exist. You can't have atoms. You can't even really have stable nuclei yet. It's just this primordial soup of subatomic particles, photons, neutrons, electrons, photons, all smashing into each other at relativistic speeds.
It's the ultimate particle accelerator, but it's everywhere.
Precisely. That's the perfect analogy. And the entire story of the universe, from that moment forward, is really a story of cooling down. It's a story of thermodynamics. You start with this unimaginable heat, and you have to wait for things to calm down enough for any kind of structure to emerge.
The timeline for that calming down is fascinating. I think people assume the Big Bang happened and then boom, stars and galaxies popped up 5 minutes later. But there was a significant lag time.
A massive lag time, an absolutely crucial one.
The source notes that the cooling process required for atoms to actually form took 380,000 years.
380,000 years. That period is called the era of recombination, and it's one of the most important moments in cosmic history.
Why? What was happening before that?
Before that 380,000-year mark, the universe was opaque. It was a fog.
A fog.
Yeah, a super hot, glowing fog. Light photons couldn't travel in a straight line for more than a few centimeters because it would immediately slam into a free-roaming electron and get scattered. It was like being inside a glowing cloud.
So you couldn't see anything.
You couldn't see anything because light was trapped. But once the temperature dropped to about 3,000 degrees Kelvin, the protons could finally capture those free electrons to form the first neutral hydrogen atoms.
And suddenly the electrons were locked up.
Exactly. And the fog cleared. The light was released, suddenly free to travel across the universe unimpeded. And that light, stretched out by 13.8 billion years of expansion, is the cosmic microwave background radiation we see today. It's the first baby picture of the universe.
So for 380,000 years, the universe was a dark, hot, dense fog. And then the lights turned on. But even now, looking at the composition of the universe today, there's a stat in here that makes me feel like we're still, well, partially in the dark.
You're talking about the breakdown of energy density.
Yes. The visible versus the invisible. The sources state that everything we can see, me, you, this microphone, the Earth, the sun, the billions of galaxies, all of that visible matter adds up to only 5% of the universe.
5%. It's the ultimate Copernican demotion, isn't it?
What do you mean?
Well, first, Copernicus told us we weren't the center of the solar system. Then we found out our solar system wasn't the center of the galaxy. Now we find out that matter, as we've always understood it, protons, neutrons, electrons, is essentially a rounding error in the final composition of reality.
A rounding error. So let's look at the other 95%. Dark matter and dark energy. I always find it fascinating that we call them dark, which sounds so ominous.
Very mysterious.
But it really just means unknown, doesn't it?
Or more precisely, invisible to light. We can't see them with telescopes. We know dark matter is there because of gravity. When we look at galaxies, including our own, they're spinning way too fast. Based on the mass of the stars and gas we can see, there's nearly enough gravity to hold them together. They should fly apart like a playground merry-go-round that's spinning too quickly.
But they don't.
But they don't. Which means something invisible, something dark, is providing the extra gravitational glue. That's dark matter, and it makes up about 27% of the universe.
Okay, so that's the glue. What's the rest? The dark energy.
Dark energy is about 68%. And it's the complete opposite of glue. It's the force that's pushing the universe apart, causing the expansion to accelerate over time.
So we're living in this tiny 5% sliver of normal matter, and we're caught in this cosmic tug-of-war between invisible glue and an invisible expansion force.
That's a perfect summary. It's a deeply humbling realization.
It really highlights that we are essentially blind to the vast majority of machinery of the cosmos. But let's focus on that 5% we can see, because the scale there is still enough to induce vertigo. Let's talk galaxies.
The great cities of the universe.
We live in the Milky Way. I think because we can see the band of the Milky Way in the night sky, if you're lucky enough to be away from light pollution, it feels familiar, but the numbers are staggering. The estimates for our home galaxy are between 100 and 400 billion stars.
Let that number sink in. 400 billion. And our sun is just one of those, an utterly unremarkable, medium-sized yellow star in a quiet suburban arm of the galaxy. If you try to count them, one star per second, it would take you over 12,000 years.
Wow.
And the Milky Way is actually a fairly standard barred spiral galaxy. It's
Yeah.
grand to us, but in the grand cosmic scheme, it's not the giant.
Right, the sources bring up IC 1101. This is one of the largest known galaxies. If the Milky Way is a standard city, IC 1101 is a continent-spanning megapolis.
It really is. The source notes it contains an estimated 100 trillion stars.
100 trillion.
It's a number that pushes the absolute boundaries of meaningful comprehension. To try and visualize the difference, if the Milky Way were the size of a dinner plate, IC 1101 would be the size of a football field. It's a supergent elliptical galaxy, essentially a massive, featureless ball of stars that is likely grown by cannibalizing hundreds of smaller galaxies over billions of years.
Speaking of cannibalizing galaxies, that brings us back home to our own future. We often think of the night sky as static. The constellations our ancestors saw are the same ones we see.
On a human timescale, yes.
But that's just because our lifespans are so short. The data shows the Milky Way is on a collision course.
With Andromeda, our nearest major neighbor.
The source says they're expected to collide in about 4.5 billion years.
It's inevitable. Gravity is pulling us together at about 110 kilometers per second. That's almost 250,000 miles per hour.
But the word collision is a bit misleading here, isn't it? People might imagine stars smashing into each other like billiard balls.
Right, and that's not what will happen.
Because space is just so empty.
So mind-bogglingly empty. The distances between individual stars are vast. So when the two galaxies merge, it's highly, highly unlikely that any two stars will actually physically crash into each other.
They'll just pass through one another.
Like two ghosts passing through a wall. But the gravitational chaos will be spectacular. It will fling stars into entirely new orbits, disrupt massive gas clouds, trigger a huge wave of new star formation, and eventually the two beautiful spirals will merge into a new, larger, more boring elliptical galaxy.
Milkdromeda, I think, is the nickname I've seen.
Let's hope future civilizations come up with a better name than that.
It's a bit of a portmanteau disaster. But the source also mentions the shape of these galaxies. 2/3 of all known galaxies are spiral-shaped. Why does the universe prefer the spiral?
It comes down to two things: angular momentum and density waves. As giant clouds of gas and dust collapse under their own gravity, they start to spin. And just like a figure skater pulling in their arms, they spin faster and faster.
They flatten out.
They flatten into disks, just like spinning pizza dough in the air. The spiral arms themselves aren't solid structures. They're actually density waves, almost like traffic jams in the stars and gas, where matter gets compressed.
A cosmic traffic jam.
Exactly. As the gas hits that traffic jam, it gets squeezed, and that compression triggers the birth of new, bright, hot stars. That's why the spiral arms are so bright. It's a structure that is just incredibly efficient for star formation.
So we've established the galactic scale. Billions of galaxies, trillions of stars. Now I want to zoom in on the engines that power these incredible structures, the stars themselves, and specifically the one that keeps us alive, our sun.
Our local fusion reactor.
The Our World in Numbers data on the sun really puts the rest of the solar system in its place. I think when we see diagrams of the solar system in school, the planets are usually exaggerated in size so we can see them.
No, massively
But
exaggerated.
if we look at mass, just pure stuff, the sun is pretty much the only thing that matters.
It is 99.8% of all the mass in the entire solar system. That's a staggering monopoly. Jupiter, Saturn, all the other planets, all the asteroids, the comets, the Earth, you, me, every building ever built, we are all squeezed into that remaining 0.2%.
We are essentially dust motes orbiting a bowling ball.
A very, very large bowling ball. And in terms of volume, the source says 1.3 million Earths could fit inside the sun.
I tried to visualize that if you had a hollow sun and you just started shoveling Earths into it like marbles into a jar.
It would take you a very long time. And yet, for all that incredible bulk and mass, it's incredibly simple chemically. The source says 91% of the sun's atoms are hydrogen, the simplest element.
It's just a giant ball of gas, but it's what it does with that gas that's so incredible. The core temperature is listed at 15 million degrees Celsius.
And that is the magic number. That is the fusion threshold. At that temperature and under the crushing, unimaginable pressure of all that mass we just talked about, hydrogen atoms are forced to fuse together to create helium.
And that process releases energy.
A tremendous amount of energy. It's Einstein's EMC2 in action. A tiny amount of mass is converted directly into a huge amount of energy.
Now, here's a number that always trips me up. We know light takes about 8 minutes and 20 seconds to get from the sun's surface to Earth.
Right. If the sun disappeared, we wouldn't know for over 8 minutes.
But the light inside the sun, the energy that's created in the core, it doesn't get out instantly.
No, not at all. Not even close. This is called the random walk problem. A photon of light created in the core can't just fly straight out. The interior of the sun is so incredibly dense that the photon travels a tiny fraction of a millimeter before it slams into a proton or an electron and gets absorbed and re-emitted in a completely random direction.
So it just bounces around.
It bounces and bounces and bounces for an absurdly long time. It can take anywhere from 10,000 to 170,000 years for that single bit of energy to drunkenly stumble its way from the core to the surface.
So you're telling me the sunlight that's hitting my face right now was actually generated in the core when early humans were just starting to migrate out of Africa?
Essentially, yes. You're being warmed by prehistoric energy.
That's incredible. And the sun itself is moving too. We tend to think of it as this fixed anchor in our sky, but it's on its own journey, orbiting the center of the galaxy. The source says it takes 220 million years to complete one orbit.
The galactic year.
220 million years. So to put that into perspective, the last time the sun was in this part of the galaxy.
We were deep in the Triassic period. The very first dinosaurs were just appearing. Mammals were tiny, shrew-like creatures hiding in the bushes. The continents were all mashed together into the supercontinent Pangaea. That was one orbit ago.
The entire age of the dinosaurs happened in one lap.
And the entire history of humanity has occurred in just a tiny fraction of the current one.
That really puts the human era into perspective, but the sun is, by stellar standards, pretty polite. It's stable. The sources, however, go into stellar extremes where things get, well, they get violent.
When stars go wild, the numbers stop being relatable and start being genuinely terrifying.
Let's talk about the supernova, the death of a massive star. The brightness stat here is just absurd. A supernova exploding 6,500 light years away could be seen during the daytime for 23 days.
Just think about that. 6,500 light years is a tremendous distance. For a single object to be visible against the full glare of our own sun from that far away implies an energy release that is almost incalculable. It would outshine the entire rest of its galaxy combined.
So what is actually happening in that moment? What creates that much light?
It's a catastrophic collapse. A massive star spends its life fusing heavier and heavier elements in its core. But when it gets to iron, it hits a dead end. Fusing iron doesn't release energy. It consumes it.
So the engine turns off.
The engine turns off. And with the outward pressure from fusion gone, gravity wins. Instantly, in a fraction of a second, the core collapses. The outer layers of the star rush inward at up to 25% the speed of light, hit that newly formed, ultra-dense core, and bounce off in the most powerful shockwave in the universe.
And that's the explosion.
That's the supernova. It releases as much energy in a few weeks as our sun will release in its entire 10 billion-year lifespan.
That's a violent way to go. But I love this next detail. We have these massive billion-dollar observatories scanning the sky, but the source highlights a discovery by a 10-year-old girl, Catherine Aurora Gray, in 2011.
Yes, she discovered a supernova in a distant galaxy.
A 10-year-old. I was barely capable of tying my shoes reliably at 10, and she's identifying exploding stars.
It's a wonderful reminder that the sky is open source. It's one of the last frontiers where dedicated amateurs can still make incredible discoveries. If you have patience and a sharp eye, you can contribute to the data set.
It's fantastic. Now, what gets left behind after the explosion is where the physics really breaks. Neutron stars.
My absolute favorite celestial object.
The density stat here is the one I bring up at parties. A tablespoon of a neutron star would weigh 900 billion kilograms.
It sounds like a made-up number. It doesn't feel real.
The source compares it to the weight of 150 Great Pyramids of Giza. All of that mass, crushed into a single spoon.
To understand that, you have to remember what atoms are mostly made of. Empty space. If an atom were the size of a football stadium, the nucleus would be a tiny marble on the 50-yard line. The rest is just electrons whizzing around in a vast emptiness.
Okay.
In a neutron star, gravity is so strong, it overcomes the forces that keep atoms apart. It crushes the electrons into the protons, turning them all into neutrons. The stadium collapses down to the size of the marble. It is matter with absolutely no empty space left.
So it's not just heavy rock. It's a fundamentally different state of matter.
It's called degenerate matter.
Yeah.
And if you could somehow bring that tablespoon to Earth and drop it, it wouldn't just sit on the table. It would fall right through the table, through the floor, through the crust of the Earth, and plunge straight to the planet's core.
And these things are spinning, right?
Oh, are they ever? Because of the conservation of angular momentum. When the massive, slowly spinning star collapses, it spins up, just like a figure skater pulling in their arms. The fastest known pulsar, which is a type of rapidly spinning neutron star, spins 716 times per second.
716 times a second. That is faster than the blades of a kitchen blender.
But it's an object the size of a city, with more mass than our sun, spinning at that speed. The surface velocity is a significant fraction of the speed of light. The magnetic fields are trillions of times stronger than Earth's. It is an environment of absolute, mind-shattering extremes.
But the universe has range. We have the hot and fast, and we also have the cold and, well, confusing, the coldest star.
The brown dwarfs. The failed stars.
The source mentions one called WISE 1828 plus 2650. Its surface temperature is only 52 degrees Celsius.
Which is 127 degrees Fahrenheit.
That's a hot summer day in Death Valley. Or a nice cup of tea.
Exactly. Brown dwarfs are fascinating because they're the missing link between a giant planet like Jupiter and a small star. They form like stars, collapsing out of gas clouds, but they just didn't have enough mass, enough gravitational squeeze to ignite sustained hydrogen fusion in their cores.
So they just fizzle out.
They burn a bit of deuterium, which is a heavier isotope of hydrogen, for a while. But then they just fizzle. They sit there, glowing faintly in the infrared and slowly cooling down over trillions of years.
It's bizarre to picture a star that you could theoretically walk on without being incinerated instantly. I mean, the gravity would crush you into a two-dimensional smear, but you wouldn't burn.
You'd be a very flat but thermally comfortable pancake.
Let's move a little closer to home. Section 3. The solar neighborhood.
The suburbs of the Milky Way.
We've talked about the sun's dominance in mass, but the planets themselves have their own gravitational quirks. Jupiter is the king.
It is so nearly a star itself. If it had been about 80 times more massive when it formed, it would have ignited fusion, and we'd be living in a binary star system.
Wow, and the gravity stat really drives that home. If you weigh 50 kilograms on Earth, or about 110 pounds, you'd weigh 126.4 kilograms, or 278 pounds on Jupiter.
And it's that massive gravity well that actually protects life here on Earth. Jupiter acts as a cosmic vacuum cleaner.
A bouncer for the inner solar system.
That's a great way to put it. It sucks up or deflects countless asteroids and comets that might otherwise be on a collision course with us. We owe Jupiter a lot.
Good looking out, Jupiter. Now, Saturn. Everyone loves the rings. They're iconic. But the dimensions of the rings are what's really shocking when you look at the ratio.
They are, by far, the flattest structures in the known universe.
The source says they're 280,000 kilometers wide, but on average, only about 100 meters thick.
Think about that ratio. If you made a scale model of Saturn's rings out of a standard sheet of printer paper, and you made the model as wide as a football field, the paper would still be thousands of times too thick.
That's insane. And what are they made of? Just rocks and dust?
Mostly water ice. Billions of chunks ranging from tiny grains of dust to pieces the size of a house, all orbiting Saturn in this incredibly thin plane. They're most likely the shattered remains of a moon that got too close to Saturn and was ripped apart by its tidal forces.
So it's a beautiful, glittering, celestial graveyard.
A very poetic way to describe it.
Let's hop over to Mars. We have this cultural obsession with Mars as a future home for humanity, but the real estate there is aggressive.
The geology is supersized, and that's largely because Mars lacks active plate tectonics.
What does that have to do with it?
On Earth, the tectonic plates are always moving. So a volcano forms over a hot spot in the mantle, but eventually the plate moves it away from the hot spot and the volcano goes extinct. On Mars, the crust just stayed still. So the lava from a single hot spot just kept piling up in the same place for hundreds of millions of years.
Resulting in Olympus Mons, a volcano that is 25 kilometers high, 3 times the height of Mount Everest.
It's so large that it actually punches through most of the thin Martian atmosphere. If you stood on the summit, you'd be in a near vacuum looking down at the clouds.
And it's not just the mountains, the canyons too. Valles Marineris. It's 5 times longer and 4 times deeper than our Grand Canyon.
It's a scar across the face of the planet. If you placed it on a map of the United States, it would stretch from New York City all the way to Los Angeles. It makes the Grand Canyon look like a roadside ditch.
We have to mention Pluto. I know, it's a dwarf planet now. But the naming story is just delightful.
It wasn't some committee of bearded, pipe-smoking astronomers.
Nope. It was an 11-year-old girl from England named Venetia Burney. She was interested in classical mythology and suggested the name to her grandfather, who passed it along to an astronomer friend.
And they loved it.
They loved it. And for naming a whole new world, she won 5 pounds.
Which, to be fair, in 1930 was a decent amount of pocket money. But yes, considering it's a world billions of kilometers away, it seems like a bit of a bargain for the Royal Astronomical Society.
And the reclassification. Pluto was a full-fledged planet for 76 years before getting demoted. People were upset.
It's a matter of definitions. We started discovering other objects out in the Kuiper Belt, like Eris, that were similar in size to Pluto or even more massive. So astronomers had a choice. Either Pluto isn't a planet, or we suddenly have to add dozens of new planets to the list.
I'd be okay with 50 planets. Memorizing the mnemonic would be a lot harder, though.
Okay.
Let's talk about our constant companion, the moon.
384,400 kilometers away on average.
Which is, by a wonderful cosmic coincidence, the perfect distance to create total solar eclipses. The sun is 400 times bigger than the moon, but it's also 400 times farther away, so they appear the same size in our sky.
A beautiful bit of celestial symmetry.
But that distance is changing.
It is. The moon is leaving us.
Slowly. The source says 3.78 centimeters per year.
And that number might seem random, but the source makes a great comparison. It's roughly the same speed at which your fingernails grow.
Wait, that's the second time we've heard that speed. The tectonic plates, too. That's bizarre.
It is a strange coincidence.
So every time I clip my nails, the moon has drifted that much further away. Why is it leaving?
It's all about tidal friction. The moon's gravity pulls on Earth's oceans, creating the tides. That constant dragging of water across the seabed actually slows down Earth's rotation by a tiny amount, making our days slightly longer over millions of years.
Okay.
To conserve angular momentum in the whole Earth-Moon system, if the Earth slows down, the moon has to compensate by moving into a higher, slower orbit. It's a gravitational trade-off.
Physics always demands balance. Now, we've been there. 12 humans walked on its surface. They brought back 382 kilograms of moon rocks. But I just love the human touches they left behind. Alan Shepard playing golf.
Hitting 2 golf balls with a modified 6-iron he snuck on board.
He claimed they went miles and miles.
And in 1/6 gravity with no air resistance, he probably wasn't far wrong.
We can't talk about space without talking about the sheer, brutal difficulty of getting there. The rocket equation is a tyrant. The Saturn V rocket weighed 2.8 million kilograms at launch.
The source visualizes this as more than 450 elephants. Imagine a tower of 450 elephants, and you have to lift all of them off the ground. The fundamental problem with rockets is that most of their weight is just fuel. So you need more fuel just to lift the fuel you're already carrying. It's a vicious exponential curve.
But once you finally get up there into orbit, your biology starts to get weird. The spinal relaxation thing is crazy.
The astronauts can grow up to 7.6 centimeters or 3 inches taller in space.
3 inches?
Yeah. Gravity on Earth is constantly compressing the gelatinous discs between your vertebrae. In microgravity, that pressure is gone, and they expand.
So you come back to Earth taller, but it hurts, right?
It can be quite painful as your spine recompresses, yes. Yeah. And unfortunately, you shrink back down to your normal height within a few days.
The International Space Station is such a fascinating habitat. It orbits the Earth 16 times a day.
Which means the astronauts on board see a sunrise or a sunset every 45 minutes. It plays complete havoc with their natural circadian rhythms. They have to adhere to a very strict schedule based on Greenwich Mean Time just to stay sane.
And we have to mention the littering incident, Skylab.
1979. The first American space station. Its orbit decayed faster than expected, and it deorbited, uncontrolled.
Debris scattered all across a remote part of Western Australia, and the local government, the Shire of Esperance, issued NASA a fine.
A $400 fine for littering.
Which NASA just ignored for decades.
They did. I believe a California radio show host eventually raised the funds and paid it off on NASA's behalf in 2009. As a joke. But shows that even if you're a space agency, you can't just go around dumping your trash in Australia.
Finally, for this section, the Voyager probes. The furthest human-made objects from Earth. Voyager 1 is over 23.5 billion kilometers away now.
It has crossed the heliopause. It has officially left the sun's magnetic bubble and is now in interstellar space. It is tasting the wind from other stars.
And it carries the golden record. Greetings in 55 languages. 115 images of life on Earth. Music from Mozart to Chuck Berry.
It's a message in a bottle, cast into the cosmic ocean. The odds of it ever being found by another intelligence are astronomically low, but it says something profound about us that we sent it anyway. It's an act of incredible, profound optimism.
We were here and we made music.
Okay, let's bring it all back down to the ground. Section 4. Earth. The blue marble.
The only rock we know of that can support a podcast.
The basic stats on Earth are surprising because we think we know them so well. We all learn it's the water planet. but the amount of usable water is vanishingly small.
Right. About 97% of Earth's water is saltwater. Of the 3% that's fresh, the source says 70% of that is locked up in ice caps and glaciers. So the water we actually use in rivers and lakes is a tiny fraction of the total.
Which is a terrifying number when you start thinking about the current melt rates. But let's look inside the planet. We walk around on this nice, cool, solid ground, but the Earth is really a heat engine. The inner core is 5,500 degrees Celsius. That is, for all intents and purposes, the same temperature as the surface of the sun.
So we are separated from a sun-hot ball of solid iron by about 3,000 kilometers of rock and liquid metal.
And that heat is absolutely critical for life. It drives the convection currents in the liquid outer core, which generates our magnetic field that protects us from solar radiation. It also drives the convection in the mantle, which moves the tectonic plates.
And a cold Earth would be a dead Earth.
A cold, dead Earth, just like Mars.
And the atmosphere itself is crucial. Without it, the source says the Earth would be 33 degrees Celsius colder on average.
That's the natural greenhouse effect. We talk all the time about the enhanced greenhouse effect from human emissions causing climate change, which is bad. But the baseline greenhouse effect is essential. Without it, the entire planet would be a frozen ice ball.
Let's talk more about that moving ground, tectonic plates. We mentioned the moon moves away at the speed of fingernail growth. The plates do too.
2 to 7 centimeters a year. It seems completely negligible. But geology plays the long game. Give it 1,000,000 years and you open up an ocean. Give it 50 million years and you shove the entire subcontinent of India into the underside of Asia and create the Himalayas.
But sometimes all that movement happens at once. The violent Earth stats here are intense. The 1960 Chile earthquake, magnitude 9.5, the strongest ever recorded.
The scale of energy released in an earthquake like that is hard to comprehend. It's the equivalent of millions of atomic bombs worth of energy being released in minutes. But the physical displacement is what gets me. The source notes that the entire city of Concepcion moved 3 meters to the west.
You go to sleep one night, and when you wake up, your house, your street, your entire city has jumped 10 feet to the left.
It permanently altered the geography of the Chilean coastline. It was a planet-altering event.
And volcanoes, Krakatoa, 1883.
The sound heard round the world.
And that's not a metaphor. The explosion was literally heard 3,000 kilometers away.
That is the equivalent of an explosion in Dublin being clearly heard in New York City. The atmospheric pressure wave from the blast circled the entire globe multiple times.
But my favorite volcano story in the notes is Paracutin.
Ah, the cornfield volcano.
This happened in Mexico in the 1940s. A farmer, a man named Dionisio Pulido, is out working in his cornfield. He sees a crack open in the ground. Smoke starts coming out.
He apparently tried to cover it up with rocks and dirt.
Which, as you can imagine, didn't work. Within a single day, it was a smoldering mound. Within 1 year, it was a mountain 336 meters tall.
It eventually grew to over 400 meters and buried 2 entire towns. It's an incredible reminder that geology isn't just something that happened in the distant past. The Earth is still being built. It's under construction right now.
And existing mountains are still growing. The source says Everest grows about 5 centimeters a year because of the ongoing collision between India and Asia. But it also makes a great distinction between highest and tallest.
This is a fantastic bit of trivia. Everest is the highest point above sea level. No question.
But the volcano Mauna Loa in Hawaii,
If you measure it not from sea level, but from its true base on the deep ocean floor,
it's 17,170 meters tall. It absolutely dwarfs Everest, but most of it is hidden underwater. It is a true hidden giant.
it's a shield volcano built up by layer after layer of flowing lava over millions of years.
Okay, let's move to our final section, and my favorite, Section 5, Natural Wonders in Life.
Where the numbers get messy and beautiful and just plain weird.
We tend to think of biology as squishy, but there is some incredible physics going on here too. Let's start with the sailing stones of Death Valley.
Racetrack playa, a classic geological mystery.
For decades, people would find these heavy rocks, some weighing up to 300 kilograms, with these long, gouged-out trails behind them in the dried mud, but no one ever saw them move.
And the theories range from high winds to magnetism to, of course, aliens.
Naturally, it's always aliens.
But the real answer, which scientists only figured out recently with time-lapse cameras, is so much more elegant. It requires a very rare combination of conditions. First, enough rain has to fall to flood the playa with a shallow layer of water.
Okay.
Then, overnight, the temperature has to drop just enough for that water to freeze into a very thin sheet of windowpane ice. When the sun comes up, the ice starts to melt and break into large floating panels. Then all you need is a light wind.
And the wind pushes the ice sheets.
Exactly. The wind pushes these huge ice panels, which act like sails, and the panels shove the rocks in front of them, scraping those long trails in the soft mud underneath.
It's a wind-powered ice conveyor belt for rocks.
Nature is a clever engineer.
Speaking of engineering, let's go to the Cave of Crystals in Mexico.
The Naica mine. This place is otherworldly.
The source says it contains selenite crystals that are 11 meters long and weigh up to 50 tons.
They're the largest natural crystals ever found. They look like something out of a science fiction movie set on Superman's home planet. They formed over hundreds of thousands of years in mineral-rich water that was kept at a perfectly stable, high temperature.
But the conditions to visit are brutal, right?
Absolutely lethal. It's 58 degrees Celsius, that's 136 Fahrenheit, and nearly 100% humidity. You would die from heat stroke in minutes without a specially designed cooling suit. It's a beautiful death trap.
Let's talk about longevity. Trees. The Methuselah tree.
The Great Basin bristlecone pine. Officially, 853 years old.
Let's put that in context. When that tree was a sapling.
The Egyptians had not yet built the Great Pyramid of Giza. The Bronze Age was just beginning. The last populations of woolly mammoths were still alive on an isolated island off Siberia.
That tree has stood on that one mountain through the rise and fall of almost every single civilization in recorded history, and it's still there.
Its exact location is kept a closely guarded secret, crucial for its protection from vandalism.
Then we have baobabs. They can live up to 3,000 years, but the pollination fact is what really caught my eye.
Bats.
They are pollinated by bats.
It makes perfect sense when you think about it. In the African savanna, you use what's available. The huge white flowers open at night, they reflect the moonlight, and they produce a ton of nectar to attract fruit bats. It's a beautiful symbiotic relationship evolved over millions of years.
But nature can also be incredibly violent. The sandbox tree.
Hurocrepitans. Do not plant this in your garden. I repeat, do not plant this.
It has exploding fruit pods.
It uses a method called explosive dehiscence. As the pumpkin-shaped fruit dries, it builds up immense internal tension like a coiled spring. When it finally reaches the breaking point, the pod bursts open with a sound like a gunshot.
And the speed.
The shrapnel-like seeds are launched at up to 252 kilometers per hour.
That's 157 miles per hour. That is a projectile weapon.
It is. It's a way to ensure the seeds get far enough away from the shade of the parent tree to find their own light. But yes, it can seriously injure people or animals that happen to be nearby.
From the violent to the tiny. The dwarf willow.
Selica serbacea.
The world's smallest tree. Maximum height, 6 centimeters.
It's a brilliant evolutionary adaptation to living in the harsh Arctic and alpine environments. If you grow tall in those places, the constant freezing wind will kill you.
Yeah.
But if you hug the ground and stay within the thin boundary layer of air right near the soil, you stay much warmer and protected. It's a tree that has learned to duck.
A very smart tree. But we are losing the big ones. The deforestation stat in our research is probably the heaviest number in this entire deep dive.
In 2019, the world lost an area of primary rainforest the size of a football pitch every 6 seconds.
Every 6 seconds. That pace is just relentless. It's hard to visualize, but just in the time we've been talking about this single point, another one is gone. And another.
It is a crisis of numbers. But numbers can also show resilience and hope.
The India record.
Uttar Pradesh, 2016. A massive state-sponsored planting initiative.
They planted 50 million trees in 24 hours.
50 million. It involved over 800,000 volunteers. It shows the human scale can work in the other direction too. We are tragically good at destruction, but we are also capable of massive coordinated restoration if the will is there.
Let's end the nature section with just some weird biology. The Christmas Island red crabs.
The annual migration. An estimated 40 million crabs all move from the forest to the coast to breed at the same time.
The pictures are incredible. It looks like the entire island is moving, like the ground is bleeding red. They have to close the roads.
They've even built special bridges and underpasses for them. It's a logistical nightmare for the people who live there, but a true biological wonder.
And the glowworms in New Zealand's caves.
Arachnocampa luminosa, which is a great name, but they aren't actually worms. They're the larvae of a fungus gnat.
That's a much less romantic name.
A bit, yes. But what they do is beautiful. They hang these sticky silk threads, some up to 50 centimeters long, from the cave roof. Then they use bioluminescence, they glow, to attract other flying insects.
So the moth flies toward the light.
And gets stuck in one of the sticky threads and becomes dinner. It's a living constellation of tiny, deadly fishing lines.
A fishing line made of snot and light.
Crude, but shockingly accurate.
And finally, the Beaver Dam, the animal construction project that's visible from space.
In Wood Buffalo National Park in Alberta, Canada, it's 850 meters long, over half a mile.
Beavers, they're rodents. They built a dam nearly a kilometer long with their teeth.
They are the ultimate ecosystem engineers. They're the only other species, besides humans, that so significantly modifies its environment to suit its own needs. In doing so, they create these incredible wetlands that support thousands of other species. That dam is a multi-generational project.
Families of beavers just passing down the wrench.
Grandpa placed that log over there. Don't touch it.
So we've done it. We've gone from the 10 billion degree heat of the Big Bang to a beaver dam in Canada.
It's quite a spectrum, quite a journey through scale.
When you look at all these numbers together, what's the big takeaway for you?
For me, it's about connection and scale. We tend to compartmentalize everything. Physics is over here, biology is over there, geology is in another department, but it's all the same stuff. The carbon in that beaver's dam was forged in the core of a massive star that exploded billions of years ago. The water that the sailing stones slide on was likely delivered to a young Earth by comets during the chaotic early days of the solar system. The numbers show us that the universe is a single, continuous story.
And we are.
We are just the part of the story that somehow learned how to count.
That is a beautiful way to put it. And I want to leave the listener with one final calculation, a bit of a provocation to think about.
Let's hear it.
We talked about the number of stars. The current estimate is around 100 billion trillion stars in the observable universe.
That's a 1 with 23 zeros after it.
Mm-hmm.
A number that is functionally infinite from a human perspective.
And we know for a fact that life can and does exist on at least one planet, us. We have the Goldilocks conditions, liquid water, a stable atmosphere, shielding from radiation.
It's a rare set of variables, to be sure, but evidently not impossible.
So, purely from a statistical standpoint, if you have 100 billion trillion slot machines and you pull the handle on all of them at once.
The odds of hitting the jackpot only one single time are vanishingly small.
Exactly. So we have this universe that should be teeming with potential homes for life. We have our Voyager probe out there with our mixtape and our address. We have radio telescopes listening for any signal. And yet, all we hear is silence.
The great silence. The Fermi paradox. Where is everybody?
With 100 billion trillion stars and greetings in 55 languages on a gold-plated disc hurtling into the void, what are the odds that no one ever texts us back?
That is the question that keeps astronomers up at night. Is the silence because we are truly the first? Or is it because civilizations don't last long enough to make meaningful contact before they destroy themselves?
Or maybe they're just waiting for us to stop being so noisy so they can finally get a word in.
Perhaps. Or maybe they saw that $400 littering fine NASA got from Skylab and decided to steer clear of the solar system.
Avoided that neighborhood, they just dropped their space stations everywhere.
It's a distinct possibility.
Well, on that existential cliffhanger, I think we're going to wrap up. Thank you for taking this genie through the scale of reality with us today.
It was a pleasure to unpack the universe with you.
We'll be back next time with another stack of sources to get into. Until then, keep looking up and let's keep unpacking.